Hello? Can you hear me? Oh, can you hear me? Can you start a live stream? You are live? Okay. I'm hearing myself. Okay. Okay, let's go. So hello everyone. I'm Geraldo. Today we are going to talk more about your favorite topic, which is memory-centric computing. We are going to already cover a lot on this subject. So today I'm going to try to give a more deep dive on some of the topics that he already covered. And I'm also going to announce and show what you need to do for Lab 3, which is going to be online. The handout is going to be online later today. So you're going to have a lot of fun messing around with memory-centric computing. So just a really, oops, I cannot click. Okay. A really brief self-introduction. So I am Geraldo. I'm a PhD here in Safari Research Group since 2018. I've been working with Onur since 2017. And I'm about to graduate, hopefully, I guess. I have dreams of that. And if you, I do research mostly on processing memory. So if you are interested on those subjects or anything that I'm going to talk on the subject here today, feel free to send me an email. I eventually get back to you because we are all honors students, so it takes time. So just a recap on what we are going to talk about here. The problem that we're trying to solve is that data movement is a bottleneck in today's systems. And I'm going to try to be quite fast here, so I'm not going to prolongate myself much, but data movement bottleneck are but the movements are bottleneck in systems for a myriad of reasons. For example, your application might not have enough data locality to make use of deep cache hierarchies or scratchpad memories on your CPU or accelerator. Your memory device or storage or your caches might not give enough memory bandwidth for your application so that you can maintain high compute throughput for your system, or maybe your latency, your trip latency to go to main memory or going to the storage, when you sum all of those latencies is too high, and then you cannot mitigate this data movement bottleneck. So even though this is not a new problem, nowadays data movement bottlenecks are becoming key in system design because we're having a push from application, and applications where the money is, and we design following that. So for example, applications like neural networks or transformers in this case have been grown exponentially over time for their data usage, and we expect that to continue increase over the years. So this trend is just going up, and it's not showing that it's going to slow down anytime soon. You also showed, Onur showed in the lecture, this work from Google that we did, that the problem is not only on servers or in big scale systems, but even your phone or your laptop, this data movement bottlenecks contribute significantly to the total energy consumption of your system, or your accelerator, for example, in a Google Edge CPU accelerator in this case. And the main problem over here that is behind these bottlenecks, both in terms of performance and in terms of energy, is that we historically have been designing systems in the compute-centric way. And this led us to design really efficient processors. So a processor doing double precision computation takes on chip, takes some picojoule of energy for you to compute. But if you need to go off chip, if you need to go to your main memory or to your storage, that is going to consume 2 to 3 more, 2 to 3 the order of magnitude of doing the complex operation. So this creates an imbalance on how we have the systems today. So we have been trying to mitigate these data movement bottlenecks in systems with many different solutions. We are still trying. Every single generation of your iPhone, you have a new and fancier hardware prefetcher that tries to predict before you access the data, if the data is, and bring the data earlier to the CPU cores. We have deeper and deeper cache hierarchies with larger and larger caches over time. So the trend of designing computer-centric architectures that tries to patch this data movement bottleneck problem is still there. It's not going to go away. But this does not fundamentally solve the problem because the fact is that we are doing computation far away from where the data resides. And one solution to mitigate this problem is to, instead of thinking in a compute-centric way, we are going to think in a more memory-centric way on designing memory-centric architectures, where we are going to move computing resources nearby the data itself. And one example that you mentioned in the lectures earlier this semester of such memory-centric architectures is what we call processing memory. So a processing memory hardware have the benefit compared to compute-centric counterpart of having access to larger memory bandwidth, abundant array parallelism, at the same time, shorter memory access latency. So if your application is going to be bottlenecked by any one of those components, probably a process memory architecture can be useful to mitigate those bottlenecks. So we also talk about the taxonomy of processing memory architectures, and we broke down processing memory architectures into two different subgroups. The first one was processing near memory architectures, and here we think about those processing memory architectures as similar to what we think about a regular von Neumann architecture, where we are going to have a distinction between logic and memory. But it's different from a compute-centric approach in a von Neumann architecture. We are going to take this logic and move it closer and closer to the memory array itself. The closer the logic is to the memory array, the larger is the memory bandwidth and the shorter memory access time that that particular logic is going to be able to take advantage of. The second approach that we mentioned in the lecture was processing using memory architectures. And here, the process is completely different from what we are used to in von Neumann architectures, because we are not going to distinguish the components of the system into computation and its memory. Here, the memory itself is going to be used for computation, and we are going to just use the analog operating principles of the memory cells themselves to perform computation. So that was an extremely fast recap of what we saw on the early lectures on processing in memory. I don't know if there's any question. I guess there was already some homeworks on that, so you should be quite sharp on processing in memory. But I guess the basic concepts are already, everyone are on the same page. So what I'm going to do today in this lecture is to elaborate more on those two subjects. And we are going to talk a little bit more in details about some processing using memory architectures that we've been designing here in Safari, and some design principles that we follow to do that design. And we are going to spend a lot of time as well talking about processing near memory architecture that we didn't spend so much time talking. And in particular, I'm going to give some focus on this lecture on explaining some of the real process memory architectures that are out there, either as prototype or as commercially available chips that you can buy in the market. And that hopefully this can motivate you to want to work on this field after your master's or your studies, because those are quite a new opportunity that is out there now in the industry, which was not the case when I started doing this 5 years ago. So it's really good for me as well. Starting with processing using memory. Before I talk about processing using memory, I probably already know this by heart, but I need to give you some refreshments on how DRAM is organized. Otherwise, nothing that I talk after this point is going to make any sense to you. So again, I'm going to give a really quick background on how DRAM operates and is organized. So if you have any questions related to that, feel free to ask after I'm done. So as probably you already know at this point, DRAM is hierarchically organized as a hierarchy of components. At the highest level of this hierarchy, what we have is what is called a DRAM mat. A DRAM mat is a 2D array of DRAM cells, which are horizontally connected to word lines and vertically connected through bit lines. So the word line shares a local system amplifier, and the bit line share, oh, it's the other way around. The bit line share a local system amplifier, and the word lines shares a local decoder. A collection, the next level of hierarchy, we have a collection of those DRAM mats, what we call a DRAM subarray. And a DRAM subarray share a global row decoder and a global word line, which spans across the several DRAM mats inside a DRAM subarray, and a global sense amplifier, which spans across the which share across the local system amplifiers in the DRAM subarray, and some I/O interface, which is used to move data from the DRAM mats to the outside worlds, to the memory controller, the memory channel, and the memory controller. So for you to access DRAM, two main operations is performed. The first is one activate. So when issuing activates to a given DRAM row, the data in the DRAM cells is read and amplified by the local system amplifiers. And after this data is latched and amplified by the local system amplifiers, the memory controller can issue read or write commands to that data, which brings portions of a column of the data to the global system amplifiers and eventually to the memory channel. So we also saw in the previous lectures that we can use these operating principles of DRAM, this activation command in particular, to perform some simple in-DRAM operations. So we start really simple with in-DRAM row copy operations. So the goal here is to copy one source row to a destination row without involving the DRAM with the CPU die at all. And to do that, we presented this row clone work, which proposed to issue back-to-back activations to the DRAM row to do this in DRAM row copy operations. So when you issue these row copy operations, the first activates to the first row, copies the source row to the local sense amplifier, and then the second activates asserts the word lines in the target DRAM cells, which allows the local sense amplifier to drive the data that was previously latched into the destination row, hence realizing the in-DRAM row copy operations. And also we saw that by doing so, we can reduce the latency of copying 4 kilobytes of data inside the DRAM chip from 1046 nanoseconds to around 90 nanoseconds, and also improve energy consumption significantly to do these in-DRAM row copy operations. So we also saw that we can extend this approach to do something more fancy. So we can do in-DRAM majority of 3 operations by simultaneously activating 3 DRAM rows at the same time. So when you activate those 3 DRAM rows at the same time, the 3 DRAM cells involved in the computation simultaneously perturbates the local bit line. And since what we have here is a differential sense amplifier in the local sense amplifier, this differential sense amplifier is going to pull up the voltage to the majority of the sense voltage levels in the 3 DRAM cells themselves. So in this case here, the majority of blue, yellow, and blue is blue. So again, by doing operations in DRAM majority operations like this, we can reduce the improve energy efficiency of in DRAM Boolean operations significantly compared to a baseline CPU die. And we talk about this row clone and ambit papers in details in the first Memory-Centric lecture. So hopefully you remember those. There was already some homeworks on this subject, but now you're going to elaborate a little bit more on how to improve those processes using DRAM operations by doing some more complex operations using those approaches. And next, I'm going to talk about some of those works, which is part of my PhD thesis. So the first one is SIMDRAM. Again, Onur briefly mentioned this in the lecture. And the problem that you are trying to solve over here is that, okay, we can do in-DRAM row copy, you can do in-DRAM majority operations. This is really cute, that's really nice. But can I use this? Is this useful for to accelerate my kernel that does mostly my addition or multiplication or division, right? So the problem is that we only support, before this work, we could only support some really simple primitives to do in DRAM computation, which can be useful in some workloads, but they are not widely applicable to a wide range of applications. Also, we have a limited and fixed set of operations. So we have those two primitives, right? INDRAM row copy and INDRAM majority, and that's it. So what if I want to do something else? How do I can provide a new flexible primitive for my application to use this type of framework? At the same time, we want to do minimum modifications to the DRAM circuitry itself, because if you think about it, if I want to do addition, you can just tell me, oh, just put an adder in each bit line in the local sense amplifier, and then you can do an addition, right? That is easy, and then the two first problems here are solved. But this comes at an extremely high area cost, which makes this substrate quite impracticable to be deployed in real scenarios. So at the same time, you want to keep the modifications to the DRAM chip as minimal as possible. So basically, the task that we went after to try to improve this work is to design this framework for processing using memory that allows the user to efficiently implement complex operations in DRAM in a flexible way, at the same time without modifying the DRAM architecture or minimum modifying the DRAM architecture. And the key idea of this work was SIMDRAM, end-to-end processing using DRAM framework that provides the programmer interface, the instruction set architecture, and the hardware supports to compute complex operations in DRAM using in DRAM massively parallel SIMD substrate. So for us to do SIMDRAM, we use two main key ideas. The first key idea is to use a vertical data layout for processing using DRAM data. So as probably you already know from the homeworks, data is stored in a layout in the DRAM chip in conventional systems in a horizontal data layout. So if you have a cache line of 64 bytes, you take those 64 bytes, you divide them across the, for example, 8 DRAM chips that you have in a DRAM rank, and each of those 64 bits in one DRAM chip is going to be spread horizontally within one DRAM row across many different DRAM columns. So, but the problem with that is that if you need to do some arithmetic operations that require us to move data across different DRAM columns, think about a RIP carry adder, right? Where we need to propagate a query from one bit to another bit. We don't have a way of doing that without including some logic or interconnects that would allow us to move data across the different DRAM columns, which comes to its own cost. The alternative is to not store data in horizontal data layout. We can store data as we want, and we are going to store them in a vertical data layout. So here we are going to take those 64 bits inside a single DRAM chip, and we are going to, in this case here, it's 4 bits in the example, and we are going to store all of those bits in a single DRAM column, spanning multiple DRAM rows in a DRAM subarray. Which this allows us to do is, now we can implicitly shift data using row clone operations. So if I want to move this bit here to this bit position here, I just row copy this row to this other row. So if this is this is your most significant bit, and this is your least significant bit, if I just want to propagate a query from here to here, I just copy this bit to this bit using double row activations, as mentioned in row clone. Another thing that this allows us to do is to think of a DRAM subarray as a massive parallel SIMD substrate. So if I keep doing in DRAM operations here across the different DRAM columns, what I'm doing is that I have a single instruction, this in DRAM majority operation, operating across multiple data, each data across stored in a single DRAM column. So now I can see my DRAM subarray as a single instruction, multiple data processing engine, which I have as many SIMD lanes as I have DRAM columns in a DRAM subarray. So in a DDR4 chip, we have around 65,000 DRAM columns. So it's a quite very wide SIMD engine, and you're going to see the problems of that later on. So the other key idea that we are going to use is to use majority-based computation for arithmetic. So in the prior work, in the EMT paper, the main operations that we are using there was we are doing these triple activations to realize a majority operations, but we are always setting one of the inputs to either 0 or 1 so that we could do Boolean and or operations. And we can compose, for example, a RIP carry adder using and or and not gates, right? However, since the primitive that you have in DRAM computation is fundamentally majority gates, it's much more beneficial that for us to just use majority-based logic instead of conventional Boolean algebra to compose our operation. So this enables us to have higher performance because we need fewer triple row activations to realize a given operation and higher throughput because the latency is smaller again. So based on that, we devised this three-step framework. I don't know why all of my works are three-step frameworks. For something it's never 4 or 2, it's always 3. And this framework takes as input use a desired operation from the user in the form of and or not representation of the gates. So this can be, for example, RTL version that describes the circuit. It can be a graph-based description of the circuit. Does not matter as long as it's in the form of and or not, or I can infer and or not logic based on that input. And then the first step of this framework, we are going to convert this input into input graph that only uses majority and not gates. And then what is left for me to do is basically map this graph into a sequence of in-DRAM row copies and in-DRAM majority operations. And the result of this is what we call a microprogram, which is basically a recipe that tells the DRAM chip how to realize this initial user input graph inside the DRAM for process using DRAM operations itself. So we store this microprogram as inside the DRAM chip for future use, and we add a new SIMDRAM instructions to the CPU ISA so that the user can instantiate this instruction in its application. Then during the execution of the application, the user enables or includes this intrinsic inside its application, and then we have some control unit in the memory controller that understand that this instruction is a process using DRAM instruction, fetch the microprogram, and then dispatch one by one the sequence of in-DRAM row copies and in-DRAM activations that realize that in-DRAM operations in the DRAM chip itself. So I'm going to go a little bit in details on those 3 steps next. So the first step here, as I mentioned, is just to convert the inputs and or not graph into its equivalent majority inverted graph. This can be done naively by using the same equivalence that the EMT paper uses. So if you want to do a AND gates and you only have a majority gate, you just use one of the inputs as 0, and if you want to do OR gates using majority gate, you set one of the inputs as 1. Oh, okay, it's correct. So we can so you can take our initial graph, use this equivalence here, and then each gate here is going to represent the other equivalent majority gate here. The majority not inverted version of the same circuitry. However, as I'm going to show next, if you just do this, you're not going to improve the performance of your circuitry because you have the same number of triple activations to realize this graph as to realize the other graph. But we can apply some grid algorithms. So this, think about logic simplification as you do in Boolean algebra. There is the equivalence of that for majority-based graph. So, like that, there is the Morgan law, all of those laws for Boolean-based circuitry. We have the same laws. It's not this exactly the same procedure, but it's the equivalent of that for majority inverted graph. And then we apply those laws in a greedy optimization algorithm so that we can end up with a simplified version of that same circuitry. So I'm not going to go through all of those inputs for this majority inverted graph here, but you can trust me that the output of this circuit with 4 gates is exactly the same output of this circuit here with a single gate. So here we move for doing 4 triple row activations to doing only 1 triple row activations with if we apply those circuit simplification logic on top of the initial circuitry. So just to summarize, the goal of this first step in the SIMDRAM framework is to generate this optimized majority not implementation of the desired operation. So then we move to the second step, and the goal of the second step is to generate this recipe, which I mentioned that we call microprogram, which dictates how I can implement that in DRAM, that this majority node circuitry in DRAM using in DRAM row copies and activations only. So this step is broken down into 2 tasks. The first task is to allocate DRAM rows to the inputs for each edge of that majority inverted graph. And the second task is to generate the microprogram in an efficient manner. So I'm going to briefly describe those tasks. Start with task 1, the allocation of DRAM rows to operands. And to do that, we need to consider 2 main restrictions that we have for processes using DRAM architectures. And these restrictions are actually engineering restrictions. They are not they could be lifted if you are up to pay the cost for them, but the restrictions there is that, at least for the first one, the second one is more fundamental. So the first one is that in the embed design, if you recall, we take the DRAM subarray and we divide the DRAM subarray into 3 groups of rows. The first one was the data row. Those rows just store your data. Some rows that are constant rows, so is one row that stores all ones and another row that stores all zeros, and then a subgroup of rows called B group or bitwise group, which are groups that are going to be connected to a special row decoder that allow us with a single address activates 3 DRAM rows at the same time. So, but those to simplify the design of that row decoder, we only have some few of those compute row in the DRAM subarray. So when I'm allocating the input rows for the majority inverted graph, I need to take into account that you don't have infinite or the number of rows for computations. You can think about them as registers. The number of registers that you have available for your operations is quite limited. So it's like 16 addresses, for example. The second constraint is more fundamental, and is the fact that when you do a triple row activation, this triple row activation is destructive. So if I activate the 3 DRAM cells of doing a triple row activations, the data initially stored in those 3 DRAM cells are going to be simultaneously overwritten by the output of the majority. And this happens because when you do the triple activation, the DRAM cell is connected to the local bit line, right? So because is what the activation does. And then when the local simplifier finish the amplification process, the charge restoration process is going to start automatically right after. So the data that is latched in the local simplifier is going to start being written back to those 3 DRAM cells that were involved during the computation. So if you need the data later on for future use, you need to copy it to a temporary row, otherwise you're going to destroy the data. So taking those 2 restrictions into consideration, we designed this allocation algorithm, which first maps assign as many inputs as the number of free computing rows as we have available. So you can think again, actually what we actually used for this is a register allocation algorithm that is quite common in compiler routines. I forgot exactly which one of them we use, but it's in the paper. Anyway, This is just a register allocation algorithm, and there are many of them in the literature with different trade-offs. So you pick one, and then we treat those inputs as those rows as registers, basically. The second thing that we do is that since after the tuple row activations, the 3 DRAM rows are going to have the copy of the data, we are going to use this property to, if in the following computation I need one of those inputs, I'm going to use any one of those 3 here as the input for the following up computation. And basically, this relaxes a little bit the allocation, because instead of thinking of having only one register with the outputs of my previous computation, now I have 3 registers available, and then I can use any one of those 3, which one is more convenient doing the allocation. So the second task is that now that I know how those inputs and outputs here are going to map to INDRAM rows, I can start generating the tuple row activations and INDRAM row copies that would realize this operation here. So basically, we traverse the optimized majority inverted graph, and then we generate INDRAM row copies for the input row so that we don't destroy the data, and then a majority operation for the to realize the input majority gates following tuple row activations, and finally a copy to the temporary row to the destinational row for the computation. So this should work. So this should give you a valid microprogram or a valid sequence of DRAM operations that would realize that computation inside the DRAM chip itself. But we can further optimize those by following some of the properties of that special row decoder that Embedded uses, so that we can further reduce the number of DRAM operations that you need to follow. So if you, because of some of those properties of that special row decoder, we can coalesce some of those DRAM row copies to a single DRAM row copy, and also coalesce a majority followed by a DRAM row copy into a single activation pre-charge command, because the first activates does the tuple activation, and the second activates does the DRAM row copy. So this gives us to optimize microprogram, which can do that target DRAM computation in a more efficient way. So what is left for us to do is that this operation does this computation for only 1 bit. So this, and I forgot to mention, since we are doing this computation in a vertical data layout instead of in a horizontal, we need to compute in a bit serial manner. So you go bit by bit, so row by row of your data world. And then in the end, if you have 32 bits, you're going to have to take 32 steps to get the output results that you want for the computation for addition, for example. If it's a multiplication, it's worse, because bit serial multiplication scales quadratically with the number of input bits that you have. So if you have 32 bits multiplication, you're going to have 32 to the times 32 steps for the computation. So what is left here is to generalize this 1 bit sequence of this operation that does a computation for 1 bit to n bits. If it's something as simple as addition, we can just repeat this process here as the number of bits that you have. If it's a little bit more complicated, because you might have some control, or your computation might depend on some of the bits that you just compute, you might have some control as well here inside this microprogram. So in the end of this process, what we have, as I mentioned, is a microprogram that implements these DRAM operations in DRAM, and then we store this microprogram in DRAM for future use, and we create a new CPU instructions called BBOP, so that the user can interface with this instruction in the application. So the final step then is to execute this microprogram, and then Basically, you want to do it transparent from the user. We don't want the user to, from the application, start issuing in DRAM activations, because the application does not have the ability to do that anyway. So we basically create a control unit inside the memory controller, which loads when you issue a BB obstruction, loads the microprogram for the corresponding operation, and issues the activation and pre-charge commands that realize that given microprogram one by one, and also deals with some control that is required for that. And in the end, we have the output inside the DRAM chip. So in the paper, you also discuss several system integration challenges that needs to be taken into account if you want to realize this in a real system. And the most important one, I would say, is the data transposition that needs to be happen. So as I mentioned in the beginning, here we are, for process using DRAM operations, instead of storing the data in a horizontal data layout, you need to store it in a vertical data layout. But at the same time, you don't want to store all of your data in a vertical data layout in the system. There is a reason why we store data for CPU in a horizontal data layout, because we want to exploit the memory level parallelism of your DRAM model. So we don't want to break that abstraction as well. So basically, we have this challenge now that we need to switch between SIMDRAM layout data in a vertical data layout and a CPU layout data in a horizontal data layout inside the same application. And to do that in an efficient way, we implement this transpositional unit that sits between the last level cache and the memory controller, and basically tracks objects or memory addresses that are going to be used later on for process using DRAM operations during the cache line eviction path. So if I have an address A here that later on is going to be used for processing using DRAM operations, I register the address here, and every cache line of this address that is evicted to DRAM because your application is running, right? I intercept that cache line, I transpose this cache line, and then I write that data in a horizontal data layout, in a vertical data layout. And then later on, if you need to read that same cache line from DRAM, I read the data, and then I transpose it back to the horizontal data layout and move it to the cache already in the correct format. So we did in the implement. Sorry, you have a question?
So the entire DRAM, all the data in the DRAM is transposed and stored initially, or whenever the PIM wants to be used, you transpose the data.
So it's not when the PIM is going to be used. So, and it's not also the entire DRAM that is transposed. So only the memory object. So this model assumes that you as a programmer knows which arrays, for example, are going to be later used in process using DRAM operations. So for those arrays that are going to be used for process using DRAM operations, you register its address to this object tracker here. And every time that a cache line of that particular memory array is evicted to the memory chip, we transpose that cache line, but only the cache lines that are registered here. So if I'm going to do addition, A plus B equals C, you would register A and B and C, and then the data will be transposed of A and B every time. But if there is another, if you do a sign between D and F, which has nothing to do with A and B, those data are never going to be transposed. It's going to always be kept horizontally. So this is a best effort approach, because we could have done something different, right? You could have say, right before doing the computation, I'm going to transpose the data of A and B. But this puts the transposition latency in the critical path of the computation itself, because I need to first transpose, then compute. But here, since we don't expect the entire application to be executed in DRAM, because this has own limitation, we expect that there are phases in the application, right? So you initialize your data, and then you move on with your life, and then at some point you trigger the process using DRAM computation. And then the hope here is that in that I'm moving with my life, cache lines of the data were already evicted to the DRAM chip, so I can transpose that data without putting that latency in the critical path for the process using DRAM operation, because it's going to be overlap with, I don't know, you're reading a file for something else in the application, for example.
At initialization, you would have to write data to the DRAM, assuming the new data layer.
In the initialize, when you're just initializing the data is going to be written, initialized to the traditional horizontal data layout. The moment that the data start leaving the cache, the data is going to be started being transposed, because you don't initialize data inside the DRAM, right? So we initialize data in the cache, in the CPU, in the cache first, and then eventually it start being evicted to the DRAM chip. So, sure.
For the triple carry adder, you're computing, I mean, at least in the slides here, you're computing the carry, but the same ABCN also needs to be used to compute the sum.
Yes, yes.
Now you have destruction of the data.
Yes, yes.
You have to again copy the data for computing a single sum bit again. Right?
So we don't compute it twice. So I was not clear because I didn't give the sequence for the RIP carry header. But basically, since I know that that bit is going to be used both for carry and for the sum, once I compute, I also copy to a temporary row, so that I can use it later and don't destruct the bit for the sum.
Essentially, you move A and B to the computing area twice.
We move A and B once, we move A twice because of how the circuitry is designed. But B is only moved one, A needs to be moved twice. Okay, thank you so much for the questions. So we evaluate SIMDRAM using this CPU simulator called Gen 5, and we implement, we compare it to a CPU and a GPU, and also doing the same computation you following ambit format, so using Boolean and OR operations. We also evaluate 4 configurations of SIMDRAM using 1 bank for computation, 4 banks for computation, or 16 DRAM banks for computation. So we use this 3-step framework to implement 16 different in-DRAM operations, including addition, multiplication, division, subtraction, and we use those operations to accelerate 7 real-world applications, including some neural networks and some database primitives. So in terms of the throughput for those 16 different in-DRAM operations, we see that SIMDRAM can significantly outperform the CPU, but it cannot outperform the GPU if you only use one bank for computation. But if you scale the number of banks for computation, eventually you can outperform the GPU as well. And this is aggregated across all of those 16 different operations. And you also see that it can outperform the state-of-the-art ping system at the time embeds as well. In terms of energy efficiency, the results are much better. We see that for those 16 operations, SIMDRAM outperform the 3 baseline systems for energy efficiency. And when you consider the end-to-end speed up for the 7 real-world applications, we see that SIMDRAM cannot perform the CPU, cannot perform the GPU depending on the number of DRAM banks that you enable for computation, and can outperform Ambit as well. So there are many more studies in the paper, which I guess, I don't know if it's a required reading, but maybe it is. The consultants have a question?
Yeah.
Sure.
Is there a lock that happens? Is there something that prevents the user from using the data while computation happens?
So we discussed this in the paper. This BBOP instruction is just integrated in the pipeline. So there is no need for a lock because this is not operating as a side accelerator itself. The CPU still controls everything. So this BBOP instruction is treated as any other load instruction. So it's registered in the MSHI entry, goes to the memory hierarchy, blah, 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 and eventually needs to go back to the CPU as well. So if the CPU is going to depend on that particular BBOP instruction, it's as if it's depending on a load. So it's waiting for it to move back, basically. So in that sense, this is not asynchronous to the CPU.
And also, is there a limit to the size of the program that we can execute? Because the subarray has a limited size.
Yes.
And is there a support for using multiple subarrays and moving data between subarrays?
Not in this work here. We don't, for all of those operations, the data fits or can be partitioned in a way that you don't need to move the data across the different DRAM subarrays. But we discussed in the lecture here this LISA paper, which connects the subarrays using some isolation transistors. And we can move the data using that approach, for example. So if you need to move data from one subarray to another one, because it does not, mine may not fit.
Also, the data to be large enough, right? The number of elements you're operating on, it has to be at least the size of the room, size of one room, for this to be beneficial.
It needs to be in at least the size of, yes, to be for you to, yes, to be fully utilized.
If it's smaller than one row, do you see performance loss? I mean,
I'm going to talk about this later on because it's the other work that we are going to mention. So let's take a break before I enter to the next one. And I guess I'm just going to follow the bell. So you're going to take a regular 15 minutes break until then. Welcome back, everyone. I need to hide that. Okay. So where we were? So we were doing process using DRAM operations, right? So now we can do in DRAM row copy. We can do in DRAM majority operations using embed, and we can do arithmetic operations using SIMDRAM. So if I want to make this a compute engine, can you tell me what type of operation that I'm missing? Okay. Yes, that is one for sure. But other than control. Does anyone have any idea? So how do I do a sine or cosine? Yes. So if you want to do, there is a class of all operations called transcendental functions that you can approximate using arithmetic operations, but you not necessarily can compute them, or they are tabulated. Or like because the space is, they are coming from a continuous space rather than a discrete. So the goal of this paper is to break of this PLUTO paper is to close this gap. So basically here we want to further extend the capabilities of process using DRAM so that we can do complex operations here, and complex in this case here, in particular, those that are required for transcendental functions. So the key idea of PLUTO, which is our solution for this, is a quite old idea. So instead of using arithmetic operations to do a particular computation, we are going to pre-compute that computation and store that into a lookup table, and then we are going to replace the operation with a memory read and basically a lookup table access, and then we have our output. So this is not new. This is what FPGAs does, for example, but we are going to realize that in DRAM in an efficient way, in what we call PLUTO lookup table query operation. So I'm going to illustrate how PLUTO works with a running example. So let's say that it's not necessarily a transcendental function, but the same principle applies. So let's say that you have a lookup table query where I want to return the second, first, second, and fourth prime numbers in a natural sequence. So before doing anything, I tabulate what are the sequence of prime numbers. So the first prime number is 2, the second prime number is 3, the third prime number is 5, the fourth prime number is 7. I store this in a table and I index them in order. So the root index 0 is going to point for the first prime number, which is 2. The lookup table index 1 is going to point to the second prime number, which is going to be 3, so on and so forth. Then I'm going to translate this query that I want to return into an input vector, which are indexes to this lookup table lookup table that I'm going to query. So first one here is going to indicate the second prime number. 0 here is going to indicate the first prime number. 3 is going to indicate the fourth prime number. And I want to have as an output in this output vector 3, 2, 3, and 7, which is the second prime number, the first prime number, second prime number, and the fourth prime number. So now I'm going to start mapping those structures here into DRAM structures, in DRAM subarray, and so on and so forth. So in one DRAM subarray, I'm going to have the input vector that you want to return, that you want to query in this lookup table query operation. And in another DRAM subarray, we are going to have this output vector, which is going to be the output of my lookup query operation. Then we are going to have the DRAM subarray, which is going to store this lookup table here, and we are going to append the DRAM bank with some mapping logic, which is going to compare the input or the row that the row ID that I'm currently accessing. So row 0, 1, 2, or 3, this ID, which with the inputs of the input vector. And if I have a match between the row that I'm currently accessing and one of the elements of this input vector, I'm going to assert some matching logic that connects the row buffer to the output vector, which is going to allow us to copy that data in that position to the output vector. So as I mentioned, you're going to have the lookup table stored in the DRAM subarray, and you're going to have multiple copies of that lookup table stored inside the DRAM subarray so that we can exploit the DRAM parallelism. So you can have many elements in this lookup table operation here as we have in theory DRAM as the size of the DRAM row. It's not the size of the DRAM row, it depends on the bit precision that you are using here, but you get the idea. So to operate this, we are going to create a new instruction called PLUTO row sweep. This works similar to how auto refresh operation works. So we are going to start activating each one of those DRAM rows one by one in order with a single DRAM operation. So let's see how it goes. So the first once receiving this PLUTO row sweep operation, we activate the first DRAM row, which operates as any other DRAM row activation, copies the input, copies the data in that DRAM row to the row buffer. And now my matching logic is going to start asking some questions. All of those questions happen in parallel, of course, but I'm going to show here in serial so we can understand together. So the first question is going to start, this row sweeping, the matching logic is going to start comparing the address that I'm currently activating, so address 0, with the element of my input vector and asserting the output, the matching logic in that appropriate places that we have a match. So I'm checking the first input of my input vector. So I'm currently accessing row 0. No, I'm not currently accessing row 0. So that position is not going to be asserted. I'm currently accessing row 0, which, yes, this is true. So that particular position is going to be asserted, and I'm going to copy the data from that position in the row buffer to the output vector. Am I accessing row 1? No. Am I accessing row 3? No. So no other connection is going to be made in those isolation transistors, so nothing else is going to be copied to my output vector. Okay, this activation is done. I move to the next row. Then again, this process repeats and the match logic start asking questions again. Now I'm going to have a matching between the first element of my input vector, I'm accessing row 1, and the third element of my input vector. Yes, I'm accessing row 1 again. Those positions are going to be, in the matching logic is going to be asserted, and I'm going to copy the data from my local row buffer to my output vector in those positions that were asserted. Then I move to the next row, row 2. I don't have the data is copied to the local row buffer. I have no matching in my input vector, so I'm not querying the third prime number in my lookup table query. And then I move to finally to the last one, to the third row, fourth row, index 3, and then I'm going to have a matching in the last position of my input vector. So then in the end, I have in my input vector the output of my lookup table query here. So the second prime number, loot index 1, is 3. Then the first prime number is 2, the second prime number is 3, and the fourth prime number is 7. Sure. Question?
Assuming a horizontal data.
Yes, it's just here, we went, really good question. We went back to the horizontal data layout. So this 2 here is just store like 1, 0. This is just 1, 0, 0, 0, 0, 1, 1, 1, 1, so on and so forth. Okay, so the question that would be natural to ask now is how do I implement this matching logic here? And because that would lead to different trade-offs. So because of that, we implement 3 different versions of PLUTO, which have different trade-offs for the matching logic. So the first implementation is what we call the buffer sense amplifier design, which is going to use, is exactly what I just mentioned in this example here. It's going to use some auxiliary data to store the temporary data as I progress across the different rows in the output vector. So this is just some extra flip-flop that when I'm asserting one particular row, I'm storing the matches. So here, for example, 7 here in that particular flip-flop. And after the computation is done, I copy that data in that flip-flop to the output vector. So this is one design. The second design is what we call gated sense amplifier. Here we are going to use the sense amplifier itself, of the output vector, to store that data as I progress in the PLUTO row sweep operation. But this is destructive of the data in the DRAM cell that I have here, because once I copy the data to the sense amplifier, the charge restoration process is going to happen, and then I'm going to destroy the data that was stored here in the DRAM cell. The third design is what we call gated memory cell, and here we are going to have a extra access transistor in the DRAM cell, which connects to the matching logic. So now I'm going to only destruct this data if I have a match. Before, I always destroy the data, even if I don't have the match. So all of the three designs have different trade-offs, as I mentioned, in terms of performance, energy efficiency, and area efficiency. The first design, the buffer sense amplifier one, which uses those flip-flops, being the middle design, has middle performance, middle energy efficiency, and middle area efficiency, sitting in the middle between those three. The second one, the gated sense amplifier, which again uses the cells, the amplifier to store the data, have the higher area efficiency because I'm not including any extra transistor other than the match logic, but have the lower performance and the lower energy efficiency because I need to do a lot of copies to restore the data as I go. The third design, the gated amplifier, has the higher performance and higher energy efficiency, but the lowest area efficiency because I'm including one extra, I have so many animations here, one extra transistor per DRAM cell. So that includes a lot of area cost. So basically, we cover those three designs, and depending on for which we are designing for, you can select the appropriate PLUTO design. So in the paper, we also discuss some system integration, which allow us to have some C-like code using the PLUTO APIs, which are converted to some series of in-DRAM operations, some or operations bit shifting, which are required to realize that those row copies or matching operations, and finally some execution energy which triggers the appropriate in-DRAM row activations and pre-charge to realize that computation. And for more details on those, I invite you to check our paper and this beautiful figure that I draw. So again, we evaluate PLUTO in simulation. Our simulator is available online, and in the paper we have a lot of analysis, but here I'm going to focus on performance and energy. We use PLUTO to accelerate 7 real-world applications which were not previously supported by prior works, include SIMDRAM, because I couldn't, they would require some sort of transcendental computation, so I couldn't accelerate them using prior approaches. And for synthetic workloads like that have those additional multiplication, which were supported by SIMDRAM. So here is the performance of PLUTO compared to the CPU, GPU, and we also have a processing near memory architecture. We use 3D stack memory with some logic for computation, and we see that PLUTO, depending on the configuration that we use, PLUTO can outperform those architectures with varying ranges, depends on the baseline architecture, of course. If you normalize this to area, the results are much better because the area of the CPU and GPU is much larger, and also we have significant energy savings compared to the CPU and the GPU. So this was PLUTO. There are many more details in the paper. So now we are all good. Now we have in DRAM row copy, we have in DRAM majority, Boolean operations, we have arithmetic, we have transcendental functions, right? So now I can go take my C application and map this whatever is there. I'm ready. I can map my C application to this process using DRAM application, to the process using DRAM substrate, and have great performance benefits, right? No, that is wrong. And this was actually related to some of the questions that was asked before. So the main problem that we identified with this processing using DRAM substrate is that it's actually one of also its main benefits, the parallelism. The parallelism that this system provides is really large. So when you're doing bit serial computation or even bit parallel computation using this PLUTO-like substrate, your granularity is a DRAM row. So you always need to operate at multiples of a DRAM row. So, and a DRAM row is really large, 64 kilobytes in DDR4 chips, right? The question is, do I always have multiples of 8 kilobytes of data in my C-like application so that I can fully utilize that bandwidth? And the answer is no. So basically, the way that I got to this realization was that when I was looking into the application that I would accelerate in the SIMDRAM paper, I suffer a lot to find those 7 real-world applications which could fully utilize the substrate. And then I realized that, okay, this is good for 7 applications, but this is not good for 200. Because those 200 applications, what actually happens is that applications and loops inside the application have varying degrees of parallelism. So sometimes you have sometimes you have 8 kilobytes of parallelism, and then that's perfect. But sometimes you have 1.5 times the size of the DRAM row, or 10.3 times. So what happened to that tail that is left, right? So that tail that is left is generating underutilization, and hence you're losing throughput, and you're also increasing the baseline energy consumption because you're activating DRAM rows that are only going to generate zeros, which is going to consume more power for your system. So basically, the problem that we identified in this follow-up paper that I'm just going to mention is that currently process using DRAM system suffers from this severe semi-utilization problem because the granularity of computations is fixed and rigid. It's always 8 kilobytes. The second problem is that, I don't know if you realize, but I'm always talking about computing an array. So I have one array, and I have a second array, and then I generate a third array. So what happens if I need to do a reduction? So if I have one array and I need to reduce this array into a scalar, I cannot do this computation in the substrate because I don't have communication across the different DRAM columns that would be required for that. Finally, in particular for the SIMDRAM and also from PLUTO, you need to program this as if you are programming assembly. So you need to you need to go to your code, identifying which operations are going to be good for process using DRAM computation. If we have a loop, we need to unroll this loop. We need to insert those process using DRAM operations for addition, subtraction, PLUTO operations, whatever you want to do. And this is quite, put a lot of burden in the programmer. So the programmer needs to be quite an expert SIMD programmer to efficiently use this. So to solve these problems, Onur already mentioned this in his lecture, so I'm going to be quite fast over here. I just want to give more details on the hardware design. We propose this system called MIMDRAM. So MIMDRAM uses this idea of a fine-grained DRAM for process using DRAM computation. So in fine-grained DRAM, basically, we have this DRAM subarray, and as I mentioned in the background, in the DRAM subarray, we have several DRAM mats, right? But when I activate one DRAM row, there is this global word line that propagates across all of the DRAM mats and activate all of them at once. Instead of doing that, we are going to segment this global word line. So you're going to put some isolated resistance here, which allows me when I activate a DRAM row, I only activate, my animation is broken, I only activate those DRAM mats that are going to be involved doing computation. So basically, this allows us to have a more flexible SIMD granularity. So if I have a 1.5 vectorization factor of your loop, I activate only half of my mats. I don't activate the entire the entire set of mats in a DRAM subarray for the second portions of the computation. So this improves throughput and improves energy efficiency of the substrate. So the other thing that this allows is that if I only activating half of my METs for one operation, if I have another operation that is data independent from the first one, I can use this other half of those METs to execute those remaining bits of that computation that is data independent. So now I can, instead of looking at this substrate as only as a single instruction multiple engine, I can look it as a multiple instruction, multiple engine is because I have multiple instructions operating across different DRAM METs, and at the same time operating over multiple data stored across the different DRAM columns. So the second thing that this allowed is us to do reduction. So basically, we can use that global amplifier to move data from one DRAM MET to another DRAM MET. So hence we can reduce the data into some scalar value. And finally, then it comes as it doesn't necessarily comes for free, but comes as not necessarily because we need to change the design, but usually when the size of this DRAM MET here is 512 rows by 512 columns. Depending on the DRAM organization, might be 512 columns by 1,000 rows, but it's always around that because we don't want to make those columns and those word lines too long. Otherwise, the impedance get high and the capacitance as well. So because of that, so since each column here is a SIMD lane, basically, we have 512 SIMD lanes in this single DRAM MET here. And this is the same number of SIMD lanes that you have in vector ISA structures like AVX512, exactly that. So we can reuse those AVX instructions or vector instructions for CPU ISAs and consecutively their compiler support to map code to this substrate here in a transparent way from the programmer. So I'm going to briefly talk about the hardware modifications that we do to realize this substrate. So inside the DRAM subarray, what we need to do basically is to segment that global word line that I mentioned before with some isolation transistors and some latching so that I can address each one of those DRAM METs as I want. And I need to have some selector logic to tell which one of those isolation transistors are going to be asserted during the process using DRAM computation. So the next thing that you want to do is to move the data across the different DRAM METs. And for that, I'm going to give a little bit more background on a DRAM column request. So when you're accessing a DRAM column, the data does not necessarily go straight from the to the local row buffer here to the I/O interface. It is further amplifying across across that column access path so that the signal integrity becomes higher, and then you can move the data to the memory channel in a reliable way. To do that, the DRAM chip uses some extra structure. So there are this thing called helper flip-flops here. Those are just some flip-flops that sits in the edge of the DRAM METs that once you read the DRAM column, the column data is first moved into those, what happened? Into those helper flip-flops. So I'm amplifying the signal. And then from these helper flip-flops to the global amplifier and eventually to the I/O interface. So we are going to use this global and local amplification paths that already exist in the DRAM chip to allow us to move the data within and across the different DRAM METs. So to move the data across the different DRAM METs, we are going to extend the global amplifier with some interconnect network, which allow us to move data across consecutive neighboring DRAM METs. And to move the data within a DRAM MET, we are going to basically repurpose these helper flip-flops here to basically allow us to have a temporary buffer to copy the data. So let's say that you want to copy the data from this column here to this column over here. So you read a column as is read regularly for a column request, and this is going to latch that column data in this helper flip-flop here. Next, instead of erasing this data in this helper flip-flop here, when we move to another column, we are going to keep this data in this helper flip-flop and just change the column address of to the destination column that you want to copy. And this is creating basically a path between this latch data in this helper flip-flop and the target local sense amplifier in the match structure here. And another property that we have is that the driving strength of this helper flip-flop here by design is higher than the driving strength of this local sense amplifier here. So this allows us to copy the data from this helper flip-flop to the local sense amplifier by just changing the column address. Cool.
Is this the definition of RDIMS?
Not really. So this is independent if you are using RDIMS or LRDIMS. This mechanism is employed regardless. So this is a common mechanism because basically these local sense amplifiers here, they are all of this design of this entire area here is quite area constrained, and you want to make this local sense amplifier as strong as it needs to be to barely sense the perturbation, the voltage perturbation that the cell is going to put in the bit line. So they are not, they don't want them to make them really big because that would occupy a lot of space in the MET design itself. So what they do is that they put this extra. You can think about them, at least I like to think about, it's not correct, but I like to think about them as yet another sense amplifier, which is a bit stronger than the previous one, but is only, I don't have as many of those as I have in the local sense amplifier. So the local sense amplifier here, I have 12 of them, and here I have only 4. So then I can make a stronger circuitry, but at the same time not consuming much area because I have less of them. They are DIMS, and DIMS are there as well for signal integrity, both for data and for common and address. But those are some buffers that are placed in the DIM itself. So we have your DRAM DIM, and in the PCB of the DIM, you place some extra buffers so that before we move the data is, or the column address that is amplified. And that again improves signal integrity. So hopefully is outside the DRAM chip basically. Okay, so basically we use this help of this intra match network to perform DRAM reduction operations. So basically here, what we are doing is implementing a reduction tree. So let's say that you want to reduce, reduce this the address of A and B into a single scalar. So basically, what we do, we compute the first step of that addition inside both the DRAM mats here, and then as I mentioned, we are implementing a adder tree. So then we need to move the data from one mat to another mat, and then we do again the addition, but only involving that second mat here. And then this process repeats across the different columns inside the internet, using the internet network as well. So I didn't draw the adder tree here, but hopefully when I say adder tree, you understand more or less that this is just basically, if you spread the data and then you do one adder with another adder here in one level, and then another node here, and that connects the input of the two previous ones. And then you keep repeating that in that tree structure. I should have drawn this, I just realized that now. But anyway, so hopefully it's more or less clear. What is missing now is for us to control this computation. So the control is a little bit more complex than the SIMDRAM control, because now we need to schedule different mats depending on the target med utilization for a given process using DRAM operation. So basically we have some structures for doing that. So a MET scheduler and a scoreboard to keep track on which MET are currently being used. And we replicate those control units in SIMDRAM so that they can operate independently across data-independent process using DRAM operations across the different DRAM METs in the DRAM subarray. So this is the hardware design of MIMDRAM. So in the software side, we implement some compiler passes on top of LLVM to identify loops that can be candidate for process using DRAM computation, schedule do some pre-scheduling of the computation so that I can tell my control unit that some operations need to be executed in the same mat because they are data dependent. Some operations can be executed in different mats because they have no data dependence between them. And finally, we do some code generation. So the first pass here is responsible for code identification. So basically, you're just reusing what LLVM has for loop auto-vectorization. So we take a loop, we auto-vectorize that loop, and that generates some vector instructions here. And instead of just using regular CPU vector instructions, we are going to convert those vector instructions down the line to process using DRAM operations. And this auto-vectorization engine allows us to identify what should be the target vectorization factor for that SIMD instruction. So, for example, this loop here operates over 1024 elements. So the maximum vectorization factor that we can use for this loop is this number of scalar operands that is going to be used, which is 124. So if this is 8K, for example, then you fully utilize the match, if the subarray. If it's 512, you're fully utilizing one match. And since here is 124, I know that the size of the match is 512, so I know that I need to locate at least 2 DRAM mats for that computation. So the second path, so after I vectorize the instructions, I generate the data dependency graph of those vector instructions. So let's go back to the C code. So in the C code here, A and B generate C, and D and E generate F. So those two operations here, they can operate in parallel because they are data independent. But this third operation here, C minus F, they are dependent of the two previous instructions. So they need to, so there is some data dependence here, right? So this means that this first operation and the second operations can execute in 2 different DRAM mats concurrently, but the third operation needs to wait for the 2 previous ones to execute. And so basically what we do in this scheduling routine is to identify those patterns and then use some metadata to tell the control unit later on that, oh, when you fetch this instruction and you fetch this instruction, execute them in parallel, but when you fetch the third instruction, wait and execute them in serial. And also in serial to the previous 2 ones. And also I need to identify that since I execute this instruction in one mat, in this other one, in the other one, and I have this one that depends on both of them, I need to move the data from this mat here to another mat. So we also include these data movement instructions that use those interconnects during the computation. And finally, the third path is just generating the binary code and triggering those BBOP instructions for the computation. So this MIMDRAM paper is a quite dense paper because we try to cover a lot of system support that needs to be done so that this works in a real system. And one of the key things that needs to happen is data allocation and alignment. So now I need to find a way to map to know that some given data structures are going to be placed in some given DRAM mats and needs to be aligned so that I can execute the computation while fully utilizing the substrate. So basically, I need to find a way to influence the memory allocator routine so that I can allocate data dependent not data dependent operations that are going to execute together inside the same DRAM mat and operations that are not going to be executed together across different DRAM mats. And to do that, basically we create this new pin allocation algorithm, pinmalloc. Is a pinmalloc, sorry, that basically uses huge pages. So huge pages give you this feature in the operating system that physical frames are going to be contiguous on the address space. So this is already one property, but it does not guarantee you that those physical frames are going to be contiguous inside the DRAM subarray or the DRAM row or DRAM mat, all of those things, because we have the DRAM interleaving scheme that is going to spread that frame across the different elements of the DRAM chip itself. So we need extra information. So we have this reverse engineer DRAM interleave schemes, and this is basically a function that tells me, oh, based on this address, I know how this address is going to map across the different DRAM channels, banks, columns, and subarrays and mets. If I want to for a fact allocate two arrays in the same DRAM mats, basically I need to apply the reverse of this function, and then I know how I should map those bits of the address space, and then I can compose the allocation accordingly. So this is way more involved than I'm mentioning here, but I'm not going to go into much details over here. So we again evaluate this using the Gen 5 simulator, using 12 workloads for 4 benchmark suites. So in terms of performance efficiency, when you are executing those 12 applications, we see that MIMDRAM significantly outperform the CPU, the GPU, and SIMDRAM operations. And if you have multiple applications executing at the same time, MIMDRAM can outperform SIMDRAM, because now we can execute those multiple applications across the different DRAM mats of a single DRAM subarray instead of having to spread those applications across different DRAM banks. We also compare MIMDRAM to other two processing in-memory architectures. So DRISA architecture here, this paper was published at the same exactly year that Ambit was published, in exactly the same conference, in the same session. And they do the same thing in different ways. So and while Ambit does those triple activations without incurring much area costs, Ambit's DRISA paper takes a completely different approach and go full accelerator mode. And they add some NOR gates to each bit line of a DRAM subarray, so you can do Boolean operations in DRAM. So we compare to that substrate and to another process in near memory operations, which uses a scalar LU engine at the edge of the subarray to do a scalar operations in a processing near DRAM type of substrate. And we see that MIMDRAM can outperform those architectures in terms of performance per area, because we are not incurring much performance area cost, while all of those two other ones are including extra circuitry so that we can do the computation. So there are many more results in the paper, which I'm not going to cover over here. But what I'm going to cover is what is left over there to be done. And there are things left to be done because I didn't graduate as a PhD student yet. But yeah, even after that, hopefully there are still going to be new things to be done, because Ismail needs to graduate. So have a question?
The problem with SIMDRAM was the throughput.
Yes.
How was this alleviated?
So the throughput was alleviated because we are just allocating as much SIMD lanes as the operation needs to be, as the vectorization factor that the compiler identifies. So if you, for example, if you are doing SIMDRAM and the vectorization factor of your loop is of half of 64,000, so 32,000, the SIMD utilization of SIMDRAM is going to be half. Of MIMDRAM is going to be 100%, because you only allocate those those given DRAM columns. And on top of that, we improve throughput because for the other half, we are doing something useful other than computing on zeros. Okay, so what is there to be done in process using DRAM? I'm sorry, I have another question.
The effect of the interconnect modifications, are the results that characterize or provide information on?
So all of this is based on another prior work called Figaro, which over there we did is also from Safari, and it uses something similar to move columns across different DRAM banks. And over there we did some SPICE simulations to see the latency of moving things, like basically asserting that column multiplexer, and it's the same column multiplexer. So we didn't redo it because it will be the same results, but we reference accordingly and point to that paper. Okay, so some limitations of the current substrate. So data conversion layout is a big thing that needs to be solved in this process using DRAM substrates, because at some point, if you don't have enough computation to amortize data transposition overheads, this data transposition overhead is going to dominate the execution time of your application. So this is not only true for process using DRAM, or you might think like, oh, this is an artifact of your own stupidity, like you create this problem in SIMDRAM and then just following up with this. So this is not only process like SIMDRAM or MIMDRAM that follows this protocol, and it's not only DRAM-based process using process memory architectures. So SRAM-based process using DRAM process memory architectures suffer from exactly the same problem, because they also need to transpose the data and operate in a bit serial manner if they don't want to blow up the area with interconnect. So and the same thing happens for flash-based. So it's just the execution model is an artifact of the execution model that leads to the least amount of area cost consumed for interconnects. We are already trying to solve this problem. I'm going to give a little bit of a spoiler on how this can be solved. If you just take that figure in SIMDRAM paper, figure 4, and then if you rotate your head like this, you're going to understand how that needs to be solved. It's just that, actually. I'm not going to talk much because I'm writing a paper for ISCA and I don't want to spoil myself. But it's basically how you should do it. You just flip your head. So the other problem is high latency for bit serial operations. As I mentioned here, multiplication and division scales quadratically with the number of, or the target bit precision of your computation. And this basically means that the latency is going to be quite high for those operations itself. So we also did some work together here with Mayank that look into alternative implementations of those microprograms that can lead to more efficient operations or efficient multiplications or division operations as well. Application scope is a big thing as well. So I personally try to be general purpose in my work. So you saw there is like always a bunch of benchmarks from random benchmark suites, because I'm trying to go for the general purpose scope. But the fact is that the way that industry works is by killing applications. So we need to find what is going to be the killing applications for this processing using DRAM architectures. So right now, the trend is transformers, neural networks, all of these. But the problem is that those architectures, what it does is mostly GenV operations, right? General multiple vector multiplications. And as I mentioned, multiplication sucks. So it's not necessarily a good fit for that, at least this type of substrate. But there are some works in the literature that tries to, or shows that depending on how you design the system, you actually can accelerate those transformers and with those bit serial process using DRAM architectures. But still, we need to do more work over there to improve that. We also need to do more space efficient LUT computation. So the way that we are doing the LUT computation in PLUTO is by taking the lookup table and indexing it directly, right? So this means that the size of the lookup table is going to be limited by the size of your DRAM subarray, which is not good. So if the bit width of your lookup table start to increase, then out of the blue, you're not going to fit into a single DRAM subarray. One way of solving that is by hashing. So you can hash the input and then map that hashed input into the DRAM subarray itself. We didn't look into that. We actually started looking into that, but then we didn't follow up. So this is why I'm giving a spoiler. So if you want to do that, feel free. It's not going to be on my thesis. But yeah, so you need to find a better hash mechanism for those lookup table computation. Another thing that is a spoiler is execution models for throughput-oriented execution. So in MIMDRAM, we are trying to take SIMD instructions and exploit SIMD parallelism only to execute process using DRAM computation. But SIMD parallelism only is not good enough for a throughput-oriented accelerator. We see this all the time with GPUs, which uses on top of SIMD level parallelism, also thread level parallelism. So both combined together so that they can have good enough utilization to utilize all of the SIMD cores on the GPU. So we need to move into that more throughput-oriented execution model so that we can fully utilize all of the DRAM subarrays, all of the MET, all of the banks, all of the chips, all of the models, all of the chips. It scales really quickly, right? If you fully want to use the hardware for computation. So we can do, we are working on this and we can improve those one step at a time, especially if you have to do a PhD thesis on the topic. So this is MIMDRAM and PLUTO. I don't know if you have further questions on those. Otherwise, I'm going to pull up Onur and I'm going to delay your break a little bit more. Just going to give this introduction to process near memory architectures, and then before I go to the real world, once we go to the break. So this is going to be a shift. So we are going to move from processing using memory. So might say shift, we are going to processing near memory. Now we want to add logic near the memory chips itself so that we are going to do computation. This is something that is really important to know if you want to design this type of systems, that you cannot do whatever you want. And this annoys me a lot as a reviewer sometimes, that people design processor near memory or propose processing memory architecture sometimes as if it's a silver bullet to any problem. And it's not. When you are doing processing near memory, you are operating at very trade-offs, very strict trade-offs when you're deciding which logic you're going to do for computation. So the first trade-off that you need to think about is area. So when you are designing a chip, a memory chip, and you're going to embed logic inside that memory chip, you need to always remember that your memory chip initially is not there for computation. It's there for storing, for density, storing bits. And once you start messing up with that, you are decreasing the density of the memory density of your chip. And it might look like a red hole. Okay, maybe I don't care about density. But at the moment that you are decreasing your density, you're also potentially increasing the memory bottleneck that your application might suffer, because if you don't have enough space to store your data, at some point you're going to have to move that data in and then do the computation. So at some point you're going to end up in a processor-centric setup as well. We are going to see how this realizes on the real-world applications, that real-world chips that I'm going to mention later. But one good example here is that at the time there was a hype of designing processing DRAM architectures around 2013 to 2020 using this architecture called HMC. This does not exist anymore, but still you have now these HBM chips. They are quite similar in scope, but basically those chips were those ones that we have some 3D stacking of DRAM layers with a logic-based die. And in this logic-based dies, you could put some computation. But first, you were limited in the amount of area that was available in the basic die. So in this HMC chip, for example, was 4.4 millimeters square and 312 millimeter watts per vertical partition that was called a vault for computation. So it was quite limited. And even though I tried to trace back this number here, and then I couldn't find who starts with this, but there are, even though this might not be 100% correct or traceable, is still the fact is the space is limited, and the power network is not strong enough to power up whatever you want. So you need to take that into account. The second problem is thermal constraints. So if regular, you are not used to have heat sinks on top of DRAM chips, right? The heat sink is designed for, or active cooling is designed for processors or or GPUs or something like that, right? So we want to keep the DRAM at that point as well. Otherwise, we are going to lose the energy efficiency edge of processing near memory architectures. And if at some point the processing capabilities of your chip becomes too costly and start generating a lot of hits, we need to move from passive cooling systems to more active cooling systems, which is an active research field for 3D stack architectures, for example. So this means that will be costly. So this also needs to be taken into account. The third one, and perhaps the more important one, that the reason that took us so long to have processing near memory architectures is because manufacturing logic plus DRAM is extremely difficult. And it's really difficult because those two manufacturing processes have been heavily optimized for different trade-offs that contradict each other. So logic have been heavily optimized for speeds, where DRAM have been heavily optimized for density. And if you try to implement logic using the DRAM manufacturing process, it's not that you cannot, but since the process was not designed for that, we are going to end up having a logic that is lower than if you just manufacture that same logic using the correct CMOS manufacturing process. So there is this oldish paper that does some analysis on that and shows that if you just do some Boolean gates using DRAM manufacturing process, your clock frequency of those that you can clock those gates is going to be lower than doing the same gates with logic. And we are going to see that this is going to affect a lot the clock frequency of the processing near memory hardware that you're going to manufacturers are putting out today. So this means that basically that your core, you're going to do this processing near memory architectures is great. You're going to alleviate data movement bottlenecks. But you as a designer have a really difficult task because you going against a much powerful core, your orthofolder cores or GPUs. At the same time, your hands are more or less tied because you don't have much area to spend. You don't have much power to spend. You cannot cool down the system, and whatever you design is going to be slower. So it's a really interesting trade-off point to be. Even though that might be challenging, it's feasible. So all of those works that Onur mentioned, for example, the Tesseract paper, the Google Neural Network acceleration for Google Edge TPUs, and for Google workloads for consumer devices, all of those papers, we try to deal with those trade-offs. And in the end, we can manage a design point which provides us more performance or energy efficiency compared to the baseline CPUs or accelerators. So before going to the break, we are going to talk about real processing near memory architectures next. And this is a great time to think about working on processing in memory and processing near memory in particular, because before all of before when I started doing process memory was 2017. It seems like a dream. Like I have that one day in 15 years, maybe we would have those chips available in the market. And when I graduate, I would have to work on something computing relevant to processing memory. But now is 6 years later, we have prototypes for not only memory manufacturers, but also server manufacturers that are looking into processing near memory architectures as a concrete, serious design point to accelerate key important applications in the market. So it's great for the community that this is happening right now, and is particularly great for me because I need to find a job next year. So yeah, so we are going to talk more about those processing near memory architectures when you come back from the break. Maybe we can take 10 minutes break and you back at 3:18. Okay, welcome back. So I might go a little bit over time, but if you need to leave, feel free to leave. I'm going to get at least to the lab 3 parts before we finish on time, because it's quite important, because we have to do lab 3. I just said lab 4, lab 3. But okay. So hopefully there is no, I guess there is no burning question related to what I just talked about processing memory architectures. So let's talk about some of my future employers. So starting, so the first commercially available processing near memory architecture that was publicized was this French company actually called UPMEM. So just me give you a brief historic perspective of this. So this is not the first time actually that prototypes for processing memory architectures have been proposed. There was a big project in the late 1990s, early 2000s called IEDM. Was from some people from Berkeley, and they want to do some processing near memory architectures. They actually tape out some chips, but it never actually reach commercial deployment. These UPMEM architectures is a little bit different. They manufacture the chip, and then you can actually go to their website, and you can. They have some servers, and you can buy time on the servers. You can run your application those chips. So it's out there, and like it's tangible. You can actually buy those DIMMs here, and you can use them. So this UPMEM, as I mentioned, is a startup from France. They released this they proposed this processing DRAM engines. Is a 2D based one, so it's not 3D stack memory. It's just your regular DIMMs, and inside these DIMMs you have some UPMEM chips, and inside these UPMEM chips you have both DRAM banks and some simple in-order cores. So I'm going to give some details on this architecture, and this is going to be the baseline architecture that you're going to use on Lab 3. So the UPMEM architecture follows an accelerator model. So even though we could, in theory, we could use these DRAM DIMMs for your main memory, there is not going to be the case, at least for now, because it simplifies the system integration a lot if you disjoin the address space from the pin accelerator and the main memory for your host processor. So they are going to do that. They are going to follow accelerator model where the UPMEM DIMMs are going to coexist with conventional DIMMs used for memory for your host system. So you're going to follow accelerator model, and in particular, what's called a loosely coupled accelerator. So a loosely coupled accelerator is any accelerator that requires explicit data movement from whatever host memory that you have and whatever memory that accelerator have. So one good example of a loosely coupled accelerator is GPUs. Compared to the alternative of having a loosely coupled accelerator is having a tightly coupled accelerator. So a tightly coupled accelerator, the accelerator sits in the same address space as the processor itself. A good example of a tightly coupled accelerator is vector processors that are in your CPUs. They are just sitting there as a component of your CPU die, but in theory, they are accelerators for, initially they were called MMX, multimedia extensions, I guess was the name, and they were there to accelerate some multimedia applications that in that time Intel identify as a key application. So they are going to follow, this UPMEM chip are going to follow this loosely coupled accelerator where we need to explicitly move data between the main memory and the accelerator itself. And we need to explicitly launch the kernel that is going to execute in the UPMEM chip itself. Again, as I mentioned, this kind of resembles how you would program a GPU. So this is from the initial patents that the UPMEM founders wrote and published. I don't remember the year. I think it was 16 maybe, but don't quote me on that. So this described this accelerator mode that I just mentioned here. So they over there in the patent says the SoC loads the data into the DRAM memory bank, then transfer the commands to the DRAM process. The data processed by the DRAM process starts, and when the computation is done, the SoC can access the output data from the memory bank. So this is again this pictorial picture from their initial patent deployment. So here we have their SoC that is the master. So it's your regular host CPU with the regular DDR interface, and then we are going to have the UPMEM chips here with some DRAM memory and some processor that's going to have some simple cores and also some scratchpad memory. So as I mentioned, the UPMEM-based pin systems organized as in a DIMM form factor. So it fits in the regular DIMM slot of your motherboard. So it does not require something fancy like silicon interposing, like into these tech chips that we are going to see later. And it sits alongside the main memory of your system. So a single UPMEM DIMM contains 8 or 16 pin chips, and this is going to depend on how many ranks are per DIMM. So it's going to be either 1 or 2 ranks. And inside each DRAM or each processing memory chip, you are going to have 864 megabytes of DRAM bank here called MRAM. So it's memory RAM. 8 they call DPUs, DRAM process units here, which are the cores that are going to be used for computations. So you have 64 DPUs per DRAM bank, because again, you have either 8 or 16 DRAM chips per 1 or 2 ranks. And inside the DPU, we are going to also have some instruction RAM that stores the instruction sequence that the core is going to execute, and the working RAM, which is some SRAM memory that is going to store the data that the pipeline is going to operate on top of. So you don't operate directly on the data on the DRAM bank. You need to move the data from the DRAM bank to the scratchpad memory, and then from the scratchpad memory to the registers of the CPU cores. So this is a picture of one of the things that the UPMEM people give you access to. So here we have a motherboard containing your regular CPU as SOCs, the DRAM DIMMs here that stores main memory, and the pin-enabled memory here. And in the currently in this given rank here, rack, you have in total 2,560 of those DPU processing engines across the rack. So we are going to use this vector addition example, especially later on, to illustrate how you program the system. So let's say that you have to, you want to add 2 input vectors, A and B, and generate a third input vector, C. And for you to do that, you're going to have to move the data from A and B to the MRAM in the DPUs, partition the data across the different DPUs in the system, and then partition the data inside one DPU across the different software threads called tasklets that executes in parallel inside a single DPU. Because I didn't mention about that processor inside the DPU is a multi-threaded processor. So again, this resembles a lot how we would program a GPU, and you're going to have more details on this later on in this lecture. So as I mentioned, since this is following a loosely coupled accelerator model, you need to manually transfer data between the CPUs and the GPUs. So to do that, there are 3 different types of data transfer instructions that you are going to use during the labs. The first one is called serial data transfer, and this is going to move the data between the CPU and a single DPU. So it moves the data from the main memory to one of those DPUs in one of those pin chips. The second one is a parallel transfer. So here you can move big portions of data from the main memory to a set of DPUs in parallel. And finally, is a broadcast, and this is only for CPU GPUs, not DPU CPUs. So it's only a single direction. So here we can move a single piece of a single buffer to multiple DPUs at the same time. So you're going to see how you program those data transfers in more details later on. So important thing between the UPMEM processing memory system is that there is no direct communication across the DPUs in a single DRAM DIMM. So this means that if you need to move data from this pin chip here to this pin chip here, you need to go through the CPU, copy the data to the main memory, and then write back the data to the destination DPU. Yeah, so this is important for some communication patterns like merge and partial inputs or distribute intermediate results. So all of these you require to move ping-pong the data back and forth, the CPU and the main memory. So I know that this is counterproductive compared to the goal of processing memory, but yeah, this is the first realization of their architecture, and having connections between these chips here, like in a NOC, for example, would be quite costly to implement. So, but we know that is in their roadmap. So then I'm going to give more details on the microarchitecture of this on the DPUs. So again, this is a picture from their patent that they initially published. So here we have as I mentioned, the memory bank, so the RAM bank, the MRAM. The processor, which has the instruction cache, the scratch pad memory, and the CPU pipeline. And this is so this is the same chip in a little bit more details on a cartoonish version. So we have some controls interface and DDR4 interface to communicate, to allow the CPU system to communicate to the DPU chip itself. Then we have those 64 megabytes of DRAM bank of MRAM, which stores the data. Some DMA engine which is going to allow you to move allow the pipeline to move the data between these DRAM banks to the scratch pad memory. Then we have the 64 kilobyte working RAM, scratch pad memory that the pipeline is going to read, the 24 kilobytes instruction RAM, and the 14 stages in order multi-threaded pipeline inside the single GPU. So as I mentioned, this is an in-order pipeline, and this is one of the effects that I mentioned that is a direct effect of manufacturing logic together, manufacturing logic with the DRAM manufacturing process. The frequency of this process is quite low, right? This is 400 up to 425 megahertz for an in-order core. The processor in your phone runs 4 times faster than this, right? Question?
Where does the power come from? From the DIMM slot, or there's extra power?
It's from the DIMM, it's regular from the DIMM slot, yeah.
And it's able to support enough power
for the core, yes, yeah. Yeah, so they don't have a second power up or anything. As I mentioned, this is all it's a multi-threaded processor, and you can have up to 24 hardware threads working at the same time. I'm not going to show here, but often it's not beneficial for you to have all of those 24 hardware threads work at the same time, because the pipeline state, this is fine-grained multi-threaded, so you just need as many hardware threads as pipeline stages, and most as the number of pipeline stages, so that the pipeline stages are fully occupied doing the execution. So based on some micro benchmark, we saw that actually 11 hardware threads working at the same time is enough to fully utilize the pipeline slots and achieve peak throughput. As I mentioned, we have 14 pipeline stages. Those are regular pipeline stages, not much different from what we saw in other processors: fetch, dispatch, read, some operate formatting, operations, and WRAM access and merging stage. So this processor has its own ISA instruction. It's a 32-bit ISA instruction that resembles a RISC-V like instruction set architecture, but it's not necessarily RISC-V, but it's similar. Or RISC-like, sorry, it's not RISC-V, RISC-like. And the UPMEM people extended the LLVM and the C-line compiler to allow you to write C-like code and generate the binary for this architecture. So here inside the this is again the pipeline. We are going to there's not many more interesting things over here other than how you program this, but we are going to see how to program this a little bit later in this lecture. So if you are interested in the microarchitecture aspects of the UPMEM and benchmarking and understanding how different features play along with the UPMEM architecture, I invite you to check Juan's lecture on that. And also we have put up this analysis of this real chip where we test different components and see how they perform. Yeah, so Juan gave this talk at TechCon at some point. And we also provide this benchmark treats to stress different components of the UPMEM system. It's called PRIM, and you can see the lecture online. So yeah, there are many lectures on this topic, and we got access to these UPMEM servers in Safari, and we've been using these UPMEM servers to accelerate different memory-bound applications. So we start by benchmarking the architecture, and then we start moving to more complex operations like classic machine learning training, like executing things like decision trees, k-means, or logistic regression over there, doing sparse matrix multiplication, doing, I'm going to talk a little bit more on these transcendental functions on these chips, sequence alignment, homomorphic encryption, reinforcement learning, and recently we showed this paper Impact, where it does distributed optimization algorithms over there. And also we have this upcoming paper in Micro that shows how you accelerate graph neural networks for this upmapping architecture. So yeah, so that was the upmapping architecture. I'm going to go back to do this when I get to the programming part we are going to use in your lab. So if you don't want to fully understand everything, hopefully when I get to the programming part, it's going to be a little bit more concrete. But I just want you to have an overview of the hardware design. Hopefully, is there any question related to the UPMEM? Okay, so now I'm going to accelerate a little bit because we are not going to use those architectures in the labs, but it's extremely important for you to know what is out there in the market as well as alternatives for UPMEM. So right after UPMEM, so in 2021, Samsung also came up with their own processing and their memory architectures. And here they are going to use 3D stack chips to design their processing and their memory architecture. So they showed this work on in this ISSCC conference, and they keep publishing works, and I'm going to mention as well, keep improving on this architecture and then reporting in other conferences. So as I mentioned, they are going to use 3D stack DRAM to propose in their processing their memory architecture. And as a background, 3D stack chip or HBM, which we are going to use here, hybrid bandwidth memory, is a memory chip that stacks DRAM layers in a buffer layer. So in HMC times, this was called logic layer. In HBM times, this is called buffer layer. So the buffer layer contains some I/O circuitry, some self-testing, and some test debug. So it's not there for free. It's there because some of the components of that was usually part of the memory controller was moved to this buffer layer to improve the connection between the chip and the memory itself. So to connect the different DRAM layers to the buffer layer, they use a technology called pre-silicon vias or TSVs. And this is a picture of what you have. So this is the SoC, the system in package. And here we have the HBM chips here. These circle things are the TSV connections. And this is the substrates and the connection between the host and the DRAM chip is done with something called micro bumps. That is used is this thing here that connects the host and the die in the silicon interposer. So this is a little bit different from like DIMM form factor, because this is, you cannot plug and unplug. So you put the die, you put the device in the package, and once it's there, you cannot remove it. But this is why what we will buy, for example, well, we will not buy because it's nowadays impossible to buy from NVIDIA anything because everyone bought already. But this is what you would get from a 800 NVIDIA GPU chip that uses those high HBM chips to provide high bandwidth for their high-end GPUs. So as I mentioned, the buffer layer is connected to the host via a silicon interposer, and in the HBM2 realization of this chip, what we have is what is called pseudo channels. So some grouping of those TSVs, which each one of them with 4 banks. And this is a little bit finer granularity than regular DRAM, where the transfer. This is wider because the DRAM is 64 bits, the column transfer, and here is 256 bits that is going to be used from a column read. But the row size is a bit smaller, so this is 1 kilobyte, and in DRAM, DDR4 is 8 kilobytes. So it's a trade-off because we want to have more DRAM banks, so then you can operate them more in parallel. So this is, so in the original paper, Samsung called this their pin architecture FIMDRAM. Now they keep changing their name, I cannot keep up. So it was initially called FIMDRAM, then it became HBM PIM, and now it's Aqua Bolts, and they keep appending some XL something in the ends of the design. So I don't know how many X and how many L's are there anymore. But yeah, but it's the same. They are talking about the same thing. Different a little bit from what I mentioned from this HMC-like design, where we would put the computation in the logic die. What Samsung does is a little bit different, and I guess because they are a mini manufacturer, they can do that. Is that they take out some of the memory dies that are originally in HBM2 chips, and they replace those memory dies with compute dies. So basically what you have is some regular memory dies together with some memory dies in the same chip. So this is nice because now you're not super limited by the area of the buffer die, but now your density of your DRAM chip is reduced because I guess they go from 8 gigabytes to 4. Now I'm not remembering if it's gigabytes or gigabits is one of them. It's halved basically. So that is always this trade-off, as I mentioned, right? Area, capacity, power, and density. So this is their custom implementation that they have inside, but it's not that much interesting for us. We're not circuit people. What's interesting is these block diagrams. So this is their organization of the FIMDRAM architecture. So this here we have the organization of the regular memory die for HBM2, and here we have the die for FIMDRAM architecture. So what you're going to see that is different is that between every 2 DRAM banks, they have these PCU blocks here, which is basically the core that's going to do the computation. And this core is going to be shared between neighboring DRAM banks over there. So they have some design goals that they want to maintain while designing this FIMDRAM architecture. So the first one is that this HBM chip is JEDEC compliant. So there is a specification that defines the protocol to access this memory chip. And they want to keep this protocol unchangeable. They don't want to change the JEDEC. Change JEDEC is always a mess because it's basically a contract that you do between the memory manufacturer and the processor manufacturer that dictates how that memory is going to be operated. So changing that protocol requires going to a lot of meetings and telling, I want to do this, I want to do that, and then a bunch of back and forth. So it's really complicated. So they don't want to do all of those. They want to keep the protocol as it is. So this is one, and this is going to impact how this chip is going to be operated. The second thing is that they want to minimally engineer they redesign the DRAM cell area. So this area here inside the DRAM chip is like where they make money off. So this is really optimized to density. So they don't want to change that. They don't want to move things around. So they are going to restrict themselves to adding computations to the peripherals. The peripherals are, they still don't want to do, they don't, nowadays they are more open, but like they don't like to change many things. But the peripherals are okay-ish to change, because there is, regardless, there are some decoders there are some logic. So regardless, there are some logic over there. So they are going to restrict themselves to adding computations to the peripheral of a DRAM bank, as I mentioned. So they are going to have one pin unit for each 2 DRAM banks, and those pin units are going to be fixed functional units. So these are not general purpose cores. They target application that they are having here to accelerate in these chips is gas neural network inference. So basically what they are going to design is some MAC units so that they can do MAC operations inside the DRAM chip. So this fixed functional unit here is going to be SIMD FPU, float point engine, for, again, to do this 64 bits float point operation. So for this to operate, as I mentioned, they don't want to change the protocol. So they are going to just repurpose the read and write commands to trigger process using DRAM computation. So basically, they are going to have a sequence of DRAM. The memory controller issues a sequence of the read requests, write requests to some given memory address. And based on that sequence, you trigger, you are in memory mode or you are in P mode, basically. And I'm going to talk a little bit more on those modes later on. As I mentioned, since this is in the I/O of the bank, the data in from this float point engine is going to be as wide as the number of columns, the column size of the bank. So it's 256 bytes. So if you divide this by 16, this gives 16 bits per FPU, because you have what you have is 16 of those 16 bits per FPU in the peripheral of the bank. So as I mentioned, the way to trigger this computation is by issuing some sequence of activate and pre-charge commands to some predefined or some fixed address locations in some banks. And this is going to allow you to trigger process using DRAM operations, either in a single bank, across all of the DRAM banks inside the DRAM chip. So yeah, this is called ABP mode in their nomenclature, which is going to trigger computation across all of the DRAM banks so that you can employ bank level parallelism. So this is the design of the FPU itself. So here, I think they keep changing the name, PCU now. So basically, you have the interface for the bank. So as I mentioned, this chip, the hardware is shared between neighboring banks. So you have an interface for the even bank and an interface for the odd bank. You have the control, the instructions that you are going to execute, some register file to store the data that you latch from the banks, and the SIMD engines here, either for multiplication or for addition. Again, what the target here is to do multiply and accumulate. So this is another view of the same thing. So what we have, as I mentioned here, is the command buffer, some pipeline decoder, some sequencer, and some register files. So the instruction set is quite limited because, again, we are just targeting neural network MAC operations. So they have only 9 RISC-like instructions, and those instructions are basically addition, multiplication, MAC, multiply and add. What is one done? Multiply and add, multiply and accumulate, and some data movement to move data across the global register file and the data path of the process of the SIMD processor, and some simple jump, some simple control, and no op. So this is not fancy at all. As you can see, this cannot do fancy branches or jump to a a particular fixed location. So it's quite restrictive, but again, because they are targeting a single kernel from an important application. So this is a comparison table that they have in their original paper, that they compare their architecture at the time FIMDRAM with the UPMEM pin chip. Some interesting things to look into this table is that, yeah, they are using different types of DRAM. UPMEM uses DR4, FIMDRAM uses HBM2. Okay, this is some manufacturing process that is not so interesting. The size of the chip is not half; it's 6 gigabytes per cube. So it's 6 gigabytes per cube, while UPMEM has 8 gigabytes per DIMM. It's important to say that this cube is way more expensive than a DIMM, because manufacturing 3D stack is much harder than manufacturing 2D logic, 3D DRAM. Since they are 3D stack, they have way more bandwidth per cube compared to the bandwidth inside the DIMM. Similar to what we saw before in UPMEM, the clock frequency of the processor is not so high, again, because manufacturing process logic using DRAM manufacturing processes is complicated, even for a memory manufacturer like Samsung. But overall, because of the available parallelism that they have, they achieve quite high peak throughput per cube, 1.2 teraflops per cube. And since they are targeting neural network inference, they support float point operations, in while the UPMEM pin chip mostly support arithmetic integer operations. So if you are interested on this architecture, we have more lectures on those. So as I mentioned, they keep publishing or they keep prototyping other architectures that build on top of this FIMDRAM architecture. So in 2023, they came up with this other architecture targeting specifically transformers. So it's just their plot showing that generative step in transformers is memory bound. And then they came up with this architecture that merges this HBM pin architecture together with AMD GPUs. And they showed that if they collaborative do the computation together with the GPU, this is much more beneficial than doing the computation you only using the GPU itself. So they also have implementation of similar architectures for mobile devices, generative AI on edge devices. And here they are not going to use the HBM chips anymore, because you don't embed HBM chips on small factory SoCs like a phone, but they are going to use low power DDR4X memory devices that target those architectures. So even though the memory technology is different, the architecture of the pin units is exactly the same. So some control, some float point multiplier and addition, the pin units is shared across the different DRAM banks. So they follow exactly the same organization, just change the memory technology. And again, they show some performance and energy gains compared to running the GP2 inference on their system. So they also have one solution for a scale-out system. So if you want to, if you have a model, if you want to train a model that is really large, you're going to have these memory expanders that is allows you or to your SSC to extend the memory capacity of your system in a scalable way. This is called a protocol called CXL. And here they have two setups where they add this pin logic either in the controller of this memory expander or in the memory chip itself, similar to what we just saw for the HBM2 and the low power DDR chip itself. For these ones, they don't have a design itself, it's just more conceptual, but probably should be quite similar to the other two that I just mentioned. So Samsung also have another solution for recommendational systems. And this is the IXDIM work that they published in 2021. And someone asked them about LRDIM. So this is LRDIM actually. So what they have is the DIM, and in LRDIM you have this buffer here that is used, as I mentioned, for signal integrity for both data and for the column data. So what they are going to do is that they are going to embed some simple computation to this buffer inside the DIM itself, so that they can do acceleration of accommodation on systems. So I'm not, in the interest of time, I'm not going to cover in so much details on how this works. So basically, they have this FPGA-based framework, which allow them to, this is the DIMM itself, and then inside the DIMM, they have this custom fabric here in this FPGA, and they have 2 ranks, and they are going to use this FPGA to have some logic, implement some logic to accelerate recommendational systems. And the key operation that they are going to accelerate in their recommendational systems is element-wise summation for the target recommendation application. So I'm not going to explain in much details the design of this, but what is important for you to know is that this is a custom fabric, so you can actually implement whatever you want. But since they are interested in recommendation systems, what they implement is this. The important key component is this adder array tree here, which is a SIMD-like processor that does this element-wise summation required doing the recommendation system processing. So yeah, so they also use this architecture to accelerate other things like sparse length sum and also database operations. And again, if you are interested on this architecture, I invite you to check Juan's lecture on that. So another memory manufacturer, SK Hynix, also has its own pin chip now. It's called AIM, and they also have a follow-up called AIM-X. They keep adding X on stuff. Here, what changes is, again, this is targeting neural network inference. And again, what is going to change is that they are using a different type of memory, GDDR6 memories. So those are usually high bandwidth memories utilized, for example, in GPUs. So this is the design of the chip. It's a little bit similar to the design that I just mentioned from the Samsung work. But here, different from Samsung, they have one processing engine per bank, so it does not share across the banks. And they also have some supplementary buffer that allows them to move data in and out this DRAM chip. So I was going to go through the details on this command set, but I think it's not so interesting. Basically, this is not what is important for you to understand is that this is not JDEC compliant. So they go to the extent of creating new DRAM commands so that they can trigger the computations in this architecture as they want. So yeah, so they have like these new activation instructions like activate 4 and activate 8, which activate either the rows in 4 banks at the 6 or 16 banks simultaneously. They have this processing unit here again, which uses some multipliers together with some adder tree and some accumulation and activation function to accelerate GEM and GEMV operations in a neural network kernel. Yeah, so this is the different ways of operating it. With if the inputs come from outside, if the inputs come from inside, or a combination or both, basically. So what I want to show next is this comparison table again. This is now they are comparing their design with the FIMDRAM architecture together with the UPMEM architecture. And so what's different between those three is that this is using DDR6, which is used as lower technology nodes. Their density is 4 gigabits per data process. The engine that they have. Let's look at the processing operation here. For some reason, they managed to get to a much higher frequency than both UPMEM and Samsung. They don't fully explain why. So good for them. They reached 1 gigahertz. The throughput of their system is 1 teraflops per chip. So 32 gigaflops in total if they have 32 chips in the system, and they are targeting the blood flow precision for blood flow points for neural network inference, and they have some support from several different activation functions your neural network. So yeah, so this is you can talk. They have an entire stack, computer system stack for this, including SDKs and everything, and then you can check their lecture online to learn more about that. So finally, I'm going to really briefly talk about the HBM PIM. No, the one from Alibaba. So Alibaba is not a memory manufacturer per se. They are a server provider, but they also came up with their own PIM chip, and here they are going to use hybrid bonding for stacking PIM and memory at the computation and logic at the same time. So hybrid bonding is this process. Let me show here. Where you manufacture your DRAM wafer, and then you manufacture a logical wafer in their own manufacturing process, and then you flip them, and then they have this what's called a wafer-to-wafer connection, where you use copper, I guess, to create connections from one wafer to another wafer here in this hybrid bonding setup. So this is a quite newish technology. So it's quite impressive to see that a server manufacturer is already looking to this direction. So here you're not going to, you cannot stack this, right? Because it's face to face. So you take one wafer and just glue them together. So here they are targeting this architecture for sorry, I'm going to go a little bit out of time. So if you have to go, please feel free to go. So they are targeting recommendation systems as, again, similar to the XT architecture. So again, they have a comparison to the SIMDRAM architecture and the UPMEM, and now they are using low power DDR4 DRAM instead of HBM. They are manufacturing this a little bit higher technology nodes. The density is 4.5 gigabytes per chip, and then their frequencies, again, is a bit low. Again, I don't know why so low, actually, because those are manufacturing different nodes. But what is important is that they bandwidth per capacity, whatever this metric means, is higher than the other ones. They keep dividing things around and then to show that based on this metric, something is better than the other. But anyway, but the energy is energy, right? So the energy per bit is lower compared to the other two ones, because they are using low power DDR4. So this is why. So if you are interested on this, again, check Luan's lecture on that. So finally gets to what's important for Lab 3. So in Lab 3, you're going to use the UPMEM SDK to program some kernels and measure some stuff, and then you're going to report the things that you measure. So overall, some programming recommendation that we learn over time programming this UPMEM system is that you want to, if you take your application kernel, you have your input data and your tests that you need to execute, you want to parallelize the tasks in a way that you can run those tasks in the DPU, parallel portions of this code in the DPU as long as possible, so you fully utilize them. So you also want to find data-independent blocks which the UPMEMs can operate independently, because the moment that they become dependent, you're going to have to move data from one DPU to another, and moving data like that requires you to go to the CPU, and this is going to include extra latency. So you should work with as many DPUs as available in the system. So you want to, this is again a throughput-oriented processor, and you want to use as much throughput as possible. And as I mentioned, you want to launch at least 11 software tasks, software threads per DPU, so you can fully utilize the pipeline slots of the DPU. So the way that you program this is by using a series of APIs that the SDK is providing, and here I'm going to list the key ones that you're going to use during the Lab 3. So the first one is the DPU alloc. This allocates some given number of DPUs that you want and creates this DPU set that you can operate on. So this is the syntax here. So this is just for a search to see if something fails. But basically you alloc the number of DPUs that you want. And this gives you a DPU set, which is what you're going to use later on to allocate the data. So you can allocate different DPUs in the course of the program. So you can have this, for example, in a loop, and you can allocate and deallocate as you go. And you deallocate DPUs using the DPU free, which is the equivalent of the DPU alloc, and then you pass the DPU set. So once you allocate the DPU, then you need to load the binary of your application into the DPU itself. So you point to the binary that you're going to execute, and then you load the DPU binary in the DPU set by passing that pointer itself. So you can launch different kernels onto different DPUs doing the execution of the application, for example. But you're not going to do that in the lab tree. So the data transfer that I mentioned, right? So in the DPUs, the UPMEM presentation, I mentioned that there are three different data transfers: serial to copy data from to one single DPU, parallel to copy chunks of data to many DPUs, and CPU and broadcast, which copies a single piece of data to multiple DPUs as well. So for you to use the serial data transfers, the API that you're going to use is the DPU copy to and DPU copy from, depending on the direction. So DPU copy from the host to the DPU, and DPU copy, I said wrong, to copies from the host to the CPU, to the DPU, and from copies from the DPU to the host. So for you to transfer, you need the DPU set. So here's the syntax again. For each DPU in the DPU set, what you do is you do a data copy from that given DPU, put a pointer in the heap space of the MRAM. This is the DRAM that you have. The offset that you're going to point to the MRAM. The pointer of the data that you want to copy in the host memory, and the size of the transfer that you're going to operate. So here we are copying two arrays, two buffers, A and B. So this is a linear address space. So after you copy array A, array B is going to start after the array A finishes, and then you just pass that offset to the DPU copy to function. For the DPU data transfers, we have a similar process, but we have different APIs. We have the DPU exfer to DPU or from, but you need to prepare the data beforehand because this is going to be a DMA transfer basically. So the idea is similar for each DPU in the DPU set. You do a DPU transfer. You prepare the data first to point the data, pointing to the location that you want to copy from in the host main memory, and then you push by doing DPU prepare exfer. No, it's the other one. DPU push exfer with the direction. So here you're pushing from to the DPU, but you can also push to the CPU from the DPU in the other direction. Again, you need to pass the offset inside the memory RAM. Again, it's a linear space, so the first copy, the offset is 0. The next one is after that data. So this after the data that you just copy, the size of the data, and this is always the default here. You don't need to worry about it. Finally, we have the broadcast, and for that you use DPU broadcast 2. Again, you're going to copy this data, this buffer data here, the transfer size, but you're going to copy to a set of DPUs in this case, because it's a broadcast. As I mentioned, there is no communication across the DPU, so if you need to do that, you need to go use those copies and through the host, and then you copy to another DPU set. So after that, you can launch the kernel. To do that, you do DPU launch and the DPU set, and then the launch can be both synchronously or asynchronous, depending on the parameter that you pass over here. But mostly you're going to use the synchronous one. So you can also pass parameters to the DPU. And then to do that, you use again the DPU transfers. So here, for example, the copy to, and then you pass as an argument a struct with the parameters that you want to pass to the DPU cores. Going back to the vector addition, this is the code for vector addition. So here we have the tasklet ID. This is similar to CUDA. So you have a task ID, for example. This is tasklet ID for that given kernel. You tile the data to move it to the DPU. You do the allocations of the working RAM and you have some data from the MRAM as well. You move the data from the MRAM to the WRAM explicitly, use the MRead and MRead operations here. And then finally, you can launch the kernel, and then you write back the data from the WRAM to the MRAM. So this might sound quite hectic or complicated, but you can always follow this the same recipe to whatever codes that you're going to implement in the lab. So, and this is going to be available online, so you can reference back over there. So finally, what is left for you to do is to launch the kernel. So vector addition here, and this is just a vector addition operation. So also you can synchronize the different tasklets using some synchronization routines that the SDK provides, and those are some mutex, some handshake barriers, and semaphores. And you need to use those synchronization barriers if you are implementing something like a parallel reductions, where tasklets are going to work together on a parallel reduction operation. So how you do that? You divide the data into different tasklets. You compute a local sum, but at some point you need to have one single DPU computing the final local sum here. So basically here you have accumulation variable, and once this computation is done, you move this accumulation variable and finalize the final sum in one given tasklet here, doing a SQL accumulation. So that was extremely fast description of the APIs, but I hopefully this was at least a guide for you to know which API routines you are going to use doing Lab 3. So in Lab 3, I'm going to post the handouts today. We are not going to use the real UPMEM system because they are in a server and need to buy time over there. But in the UPMEM SDK, they provide us some simulator of the UPMEM system, and this is what we are going to use. So the handout describes you how to install and use the SDK and the simulator, but you also provide some Docker container which you can just launch, and then everything's already installed, the simulator already works, and you can just start implementing your codes. So you're going to find inside the handout two template files for task 1 and for task 2. The task 1 here, you're just going to play along with those data transfer, serial, parallel, and broadcast, and they are going to measure their performance using instruction counts. And then the second task, we are going to implement simple kernel here, which basically, it performs y equals to y plus x. And then you're going to check this kernel with different data formats, and then you're going to see that in the files there is a make file, and the make file makes you quite easy. Everything's parameterizable, so you can just change the make file, compile to those different data types, and then measure the instruction counts, and then repeat that for each one of them. Finally, you're going to implement the vector reduction, and for the vector reduction, you're going to have to use the synchronization barrier. Then you have bonus portions of the lab as well that you have to implement RGB brightness kernel over there as well if you want to do the bonus. So that is for Lab 3. I don't know if there is any question for Lab 3.
Are there any architectural constraints? For example, does the Docker container run both on ARM and recipes?
I test on my computer, which is Intel, but it shouldn't have. If you just have Docker, it should just run. Yeah. And we have a Docker for Linux and for Windows as well, so it should work on both. You have a question? Okay, sorry. So this is Lab 3. It's going to be posted today in the evening after I finish here, and then the deadline is in 2 weeks, the soft deadline. So that was the main thing. So as you saw, programming these DPU systems require you to do a bunch of stuff. So you need to split the data across the different pin kernels. You need to manually transfer the data within the DPUs and the host memory. You need to manually handle caches between that MRAM and the WRAM, and you need to manually transfer your output data from pin chips to main memory. So in practice, you as a programmer are going to have to do several tests to implement something. So you need to align data within, because the data needs to be 8-byte aligned to fit inside a single DPU at a time. You're going to have to collect input parameters and transfer those input parameters to the different DPUs using those data parallel or serial data transfers. You're going to have to launch the computation, collect results from the DPUs, manage the scratch pad, so manage the data between the MRAM and the WRAM, and you're going to have to orchestrate the computation and the communication finally. And we know that all of this is quite cumbersome as part of the lab, but we have been working on trying to design frameworks that tries to aid the programmability of the UPMEM pin system. This is the DAPA framework, which we cannot use for the lab because then we don't need to do anything. But basically, this framework uses this concept of data parallel patterns to abstract away those tasks that the programmer needs to do. And basically we implement those 5 data parallel patterns here. This is called a skeleton-based program. So the user just define how data is mapped between inputs and outputs and define a modifiable function. And then basically you can combine those different parallel patterns to do some form of computation. So the way that this works is basically we have this concept of a pipeline, and this pipeline is going to allow you to do different transformation across different stages, and each stage is going to represent a different data parallel pattern. And since the data flows sequentially across different stages, the framework automatically handles those data transfers and data orchestration routines that are required in the UPMEM pin system. So this DAPA framework that we implemented compiles and executes each stage of the pipelines automatically, completely independent from the user. So the way that it does, so let's say that you want to do this target computation here. The only thing that you need to do is define the stages that you're going to be required for this computation. So in this case, is a map and a reduced stage. And then there is the framework dynamically compiles this code down to UPMEM binaries and run the application in the UPMEM pin system itself. So this is the DAPA framework that is the framework that we designed to try to reduce the complexity of programming real processing memory systems. And Onur also mentioned the simple pin architecture, which is an early implementation of the similar framework. So you also implemented this transpinlib, which is a library of transcendental functions for the UPMEM pin system, because the UPMEM hardware does not provide you hardware support for those transcendental functions themselves. So basically, we opt to create these APIs that approximates transcendental functions using either lookup tables or coordinate implementations of them. And we implement several key transcendental functions over there, and the API is available online. So this concludes I think that was the last lecture on memory-centric computing this semester. Hopefully, sorry for going over time, but hopefully you enjoyed it. Again, this is a great time to do processing memory research. There is still a lot of things to be done across the memory stack. We can do all of them one step at a time. And with this deployment of PIM in the field right now in real products, more than ever, we have a lot of great incentive to push for those memory-centric architectures. Again, next week, I'm flying to Micro, and we're going to have a PIM tutorial over there. We are going to have invited talks from other PIM researchers, and it's going to be available online on YouTube. So you're going to have, if you want to join, feel free to join. You're going to have other people talking about memory-centric computing, so you're going to see that I'm not the only one inventing all of those things from my head, because I want to have a PhD from ETH. So it's good for you to see other people talking about their own problems related to processing memory. And again, we are currently working on the new version of PIM book chapter which I need to finish now, which is going to be available soon. So thank you so much for your attention. Sorry again for going over time. And if you have any question related to Lab 3, you can post on Moodle, and I'm going to try to solve everything. Thank you, everyone. I don't know if there is any burning questions. Otherwise, we are done. Thanks so much.